A 216 meter squared rectangular pea patch is to be enclosed by a fence and divided into 2 equal parts by another fence parallel to one of the sides. What dimensions for the outer rectangle will require the smallest total length of fence? How much fence will be needed? Let W equal the width of the rectangular region and L be the length of one of the smaller sub-rectangles. Do you see how this problem differs from the previous one? There we had a fixed perimeter and we wanted to maximize the area enclosed. Here we have a fixed area and we want to minimize the materials required for construction. Given our variables length and width, we know that the total area, 216, has to equal the total length, which is 2L, times the width, W. We want to minimize the amount of fence used, so let's create a function f that's going to be 4L plus 3W. Again, solving to make this a function of one variable, let's solve for L. L is going to be 216 divided by 2W, which is 108 times W to the negative 1. Substituting into the function for the amount of fence, we get 4 times 108W to the negative 1 plus 3W. Multiplying gives us our function f equals 432W to the negative 1 plus 3W. Since length times width is a constant that's non-zero, it's not actually possible for our width to make it all the way to 0. It can be some infinitesimally small number, but then the accompanying length would have to be huge. Similarly, if the length were infinitesimally small, the width would have to become huge to make sure that we met the constant region being enclosed. What that means for this problem is that we are maximizing not on a closed interval, but on an open one, the one between 0 and infinity. We can go ahead and find the critical points by taking the first derivative. That will give us negative 432W to the negative 2 plus 3. Ideally, we like to factor, so let's start by getting rid of negative exponents. We can rewrite f prime as negative 432 divided by W squared plus 3. Get a common denominator of W squared. This will give us 3W squared minus 432 over W squared. Factor out a common 3 from both terms in the numerator. This gives us 3 times W squared minus 144 over W squared. And then factor, because we have a difference of perfect squares here, into 3 times W minus 12 times W plus 12 over W squared. So f prime is going to be 0 when W equals positive 12 or negative 12 meters. Since the width is a physical quantity, it can't be negative, and we can toss that particular value out. We also have to worry about where f prime is undefined. That's when W equals 0. But as we saw previously, 0 is not in our interval because it's impossible to have a width of 0 and enclose a specified area. That means there's a single critical point in our region of consideration, namely W equals 12. We just have to verify that this gives us a minimum fence length. I recommend the second derivative test again. So the second derivative will bring negative 2 times negative 432 to give us positive 2 times 432 w to the negative 3. Since f double prime equals 2 times 432 times w to the negative 3, on our interval of consideration between 0 and infinity, the second derivative will always be positive. This means that our critical point at w equals 12 is going to be a minimum by the second derivative test. We conclude by being sure to answer the question asked: the dimensions of the outer rectangle for the smallest length of fence and the amount of fence needed. So the minimum amount of fence occurs when w is 12 meters. The dimensions of the outer rectangle will be 12 meters by 18 meters, and the total fence needed will be 72 meters.